Okay, hello everybody. Welcome to our series of webinars where we'll be showing the capabilities of Civil FAM. First of all, I want to thank you for taking your time and for joining us in this series of webinars for Civil FAM and CAE Solutions. First of all, I would like to make a little sound test. Please, I need you to confirm if you're listening clear and with the strength enough for continuing with the webinar. You can write down in the chat and confirm that you're listening clearly. Okay, uh, I'm going to explain a little bit what is the point of this model and what is consisting, that we're gonna show here. Let's review. This is a concrete beam column joint, which is subjected to a cyclic loading, and we are going to show how to model such behaviors in Civil FAM. Okay, as you can see here in the slide, in the first photo, you can see this is a concrete beam column joint. Okay, where we define the structural elements, we defined the reinforcing using volumetric and 3D solid elements. Okay, and I would like to mention that for these models we have several behaviors that we can evaluate. For example, we can, in this graph, we can see here that there is plotted a load versus deflection curve. Okay, and on concrete frames, the stiffness of members is very sensitive. Thus, the joints are affected by concrete cracking and bond slip, for example, and the post-shielding response of columns and joint panels that are very sensitive to axial load. Under large deflection, okay, inelastic cyclic deformation, component strength often deteriorate due to fracture, crushing, local buckling, bond slip, and other phenomena. So one of the analysis that we can perform, and we all are related, is the linear elastic analysis, or called first order analysis. Well, we know that the Hooke law is applied. Strains or deflections are proportional to forces or stresses. And with this a common analysis that we always make, and we every data in our job, in our design. Okay, but as I said, when this kind of structure, concrete columns and beams, are subjected to cyclic loading, they deteriorate. They lose capacity of withstanding load, and they lose capacity of dissipating energy. And one of the models and where we can capture that behavior is what is called the first order rigid plastic, okay, that is represented for plastic hinges, okay. But we know that under large inelastic deformations, component efflorescence often deteriorate due to fracture, crushing, local buckling, bond slip, and other things, okay? And these plastic hinge models works by concentrating the plasticity in several length hinges with moment rotation, model parameters, and specified hysteretic properties. We can see here in this curve that the difference between the first elastic analysis and the behavior in the plastic hinge. But also we have another behavior, which is the P delta effect. When we take into consideration the P delta effect must be, and we know that must be modeled, as they can ultimately lead the loss of lateral resistance, what is called ratcheting. This is a gradual buildup of residual deformations under cyclic loading. Large lateral deflections magnify the internal forces and moment demands, causing a decrease in the effective lateral stiffness. And we also have, in this curve, we can see here, second order analysis, we have a loss of rigidity, we have a loss of strength, okay? And as the forces, internal forces are magnified, okay, and the lateral stiffness is decreased, with the increase of internal forces, a smaller portion of the structure capacity remains available to sustain lateral loads, leading this to a reduction of the effective lateral strength. So we have here that we have the behavior of the elastic first order analysis, we have the behavior which is modeled with the elastic hinge, and we also have, when we take into consideration the P delta effect. However, we still have, which is called the distributed plasticity formulation models, where the variations of the stress and the strain through the section and along the member are captured in more detail by means of nonlinear hysteretic constitutive properties. And all of these are captured by small finite elements, which is we are using in this model. We have defined a solid elements, and then we make automatic meshing, and all the inelastic behavior is captured by these own finite elements, micro finite elements. Okay, and well, this is a great capability that we are showing how to perform this model on SimpliFan. Okay. Now we're going to continue to take a look of the model and how we performed, how we're going to the process of modeling on SimpliFan. Okay, here you can see the model, the interface of SimpliFan. Okay, here's our model. As I told you, it was finite element, taking into consideration the distributed plasticity. Okay, in the user graphical interface, we can see here that it's very easy to handle. For example, if we want to see the model in any direction, we only can press the y-axis, for example, and the model can rotate easily. We can press, for example, if we want to see the x-axis, we go straight and we can rotate the model, as well as the z-axis. And we can see the structure from this point of view. So basically, now we're going through the modeling aspects of the model. Okay, let's talk briefly about the geometry tab. Okay, in the geometry tab, for generating any model, we have several options here, such as curves, polylines, splines, We have surfaces. We can generate triangles, quadrilateral elements, primitives, and we also can make volumes. And we have different operations options for working through these geometric characteristics. Okay? For example, we can see here in the Geometry Entity tab that this is all the information generated for the modeling process of this beam column joint. As you can see here in the properties windows, we get the information, the connectivity, the attributes for the geometry, and although you can see here a lot of information, this is done automatically. Just with a few clicks, you can generate in a very, very easy manner this, well, whatever model you want to do. Okay? Now, after you define the geometry, the next point is going through the Model tab. Okay? In the Model tab, we have two main options that where we define the materials or material properties. Okay, we have steel, concrete, reinforced steel, we got soils, and if you want to make a generic material, you can also do that. And the other sections is where you define the sections applied to geometry or structural elements. We have a steel, we have the code library, we have the concrete, we have cable elements, all of them very easy to handle and to apply to different members. Okay, and we're gonna show the material tab where for this model we defined the reinforcement material for with an FNY of 60,000 psi. Okay, here we can see the properties. We can observe the stress strain diagram, which for which the model it's going to behave. And if we have an information, our own diagram, which is coming from a test, which is coming whatever you bring in your information, you can generate your own information. If you have special considerations, you can put it here and you can apply to your model. Okay, I'm going to show you the concrete. So we defined the properties such as density, Poisson modulus, and among others. And now we have the stress strain diagrams for which we can evaluate for different ages and for different resistances. It's very easy to handle. Okay. We also can define the cracking properties. Okay, the crushing properties and whether or not the program is going to take it into account for the modeling. We also have the creep and shrinkage parameters where, in a Lindsay manner, it brings the full information, but as I told you before, you can custom your own information. Okay, so once you have defined your model, your geometry, your material, your sections, okay, you go through your mesh. Okay, in the mesh tab, we have all the structural elements that we can apply to a model. For example, beam elements, truss elements, shells, cables, and in this model, we used 3D solid elements. Okay, for the beams, we made 3D solid elements for the columns, and for the reinforcing bars, we defined truss elements. Okay, and we can see here in the Entity tab, if we go to the Entity tab, we can show in the structural elements, here we have all the elements that we defined. If we select here, we can see that this is a volume, and as you can see here, you see a lot of mesh, you see a lot of elements, but this is very easily for drawing and for generating. For example, you see the parameters of the beam 2, the mesh type, the algorithm, and the information to the proper element. Okay, we can also hide this element, and we can see how the bars, the reinforcing bars, are modeled also. Okay, so you can make your models, you can perform your modeling with a great precision, because you can put all the characteristics, all the geometry, and the real connecting. Okay, I'm gonna turn the volume on again. Okay, I would like to show that maybe you can ask, oh, okay, but how can I make the bonding in this joint? Well, this is a very powerful tool that we have here with Civil Fan, because we can simulate the contact between two or more elements using this tool. By using this tool, we only have to select one member and another member and assign them the contact property. And as you can see, the Civil Fan routine is in charge of making the meshing, the coincidation of meshing, and the contact. For example, we have different kind of contact. Okay, the type of contacts are glue contact, touching contact, breaking contact, and advanced contact. In this model, we evaluated the glue contact between the beams and the columns, and this is applied to the column on one side of the beam and the column to another side of the beam. Okay, another interesting characteristic is that how can we make the bond of the reinforcing steel to the concrete? Well, we basically have an insertion tool where we define a host element. In this case, the host elements are the beams and the columns. Okay, and we have the inserted elements. Okay, that in this case is the reinforcing bars, and we only with 2 or 3 clicks define touching one element and applying to another element, we simulate a real behavior. So we can reduce the work in only drawing and assigning properties, and Civil Fan is in charge of making all the hard work of connecting, meshing, gluing, and all of those stuffs that sometimes in other software are very uncomfortable for simulating and making that information. Okay, now Civil Fan in the display have several forms of presenting, of displaying information. Let's activate the geometric view, for example. Okay, well, there you can see the geometry element which conform the joint of those elements. Okay, you can see we have surfaces, we have volumes, we have lines or curves, and basically these are the elements that we have to draw and connect. Okay, and once we define the structural elements, the meshing, and all those stuffs, CivilFEM, the program, automatically meshes, automatically generates, and is in charge of gluing and simulating the real rigid behavior between bars, between concrete, and those elements. Okay. Well, now let's talk about the loads a little bit. How we perform the loading of these elements. If you go to the load tabs, okay, if we go to the load tab, we defined one load group, which is the force H1, for example, or the actual load, excuse me, the actual load, and we applied a load there, okay, which simulate the internal force in that portion of the column. We can hide information and see how it looks, generated. Uh, Now I'm going to show you the force, the horizontal force H1. So this is one force, a static force that we defined for simulating the lateral load, okay? And this is applied in one direction, and then we defined another set of loads, which is the lateral force H3, okay, simulating the force applying to the opposite direction. Okay, for example, I'm going to activate the force H2, for example, here. You can see here that there is no load graphically, but this step of this group of load is generated in order to simulate the point of loading when we apply the load to one side, then we discharge, okay? So a time of discharge is running, and then we load to another side that continues on load 3. Okay, now I would like to show you the boundary conditions that we specified for this model. So you can see here that is graphically represented, but I would like to go to the boundary conditions entity tab for a while. Okay, I'm gonna drop down this. So there we can see that for beams, okay, we have a constraint of the movement in X direction. We have a constraint that moves Z direction. And on the top of the column, we have a constraint of the rotation of the axis of the member. Okay? Okay, I'm going to close this tab now. And I would like to show you on the load tab, the load case. Okay, it's pretty important to know that in CivilFEM, as we perform nonlinear analysis, advanced nonlinear analysis, we have a way of introducing or defining our loads. First, we find the load case is not only created for the different load patterns that we have created or load groups, but also it includes the boundary condition. Because, as I said, we handle all the different parameters that can vary along the running of the model, and especially when we make nonlinear analysis. Okay, and we have here the load. We have in the case we have the column actual force, the force H1 lateral force going to one side, and we have defined the boundary group and the solution control. the solution control, we can define there that we have the convergence, we have the steps, and we have the frequency and the control application of load. That in this case, we're going to be applying load. It's an increasing load method, and is a linearly ramped application of loads, as we can see there. So this case start in one step, and it's going forward with applications of load. And once this load finishes, begins the load case number 2. I'm going to show you here. Okay, I'm going to open. And as you can see here, for example, that when our load case 1 has finished, okay, the amount of steps, for example, 100 steps, it finished the last one step, okay. Now we enter in a moment where the structure is unloaded because the load is going to be applied to another side. But a time has to be passed, and that's why you don't see any load. What is happening here is the time, and then we proceed to apply the load 3, the case load 3. Let me show you here. And now you can see here that once the all steps for load 2 has finished, begin the steps of load 3. And there is an increase in load. We're going through 100 points, or maybe if you want to define 50 points, or the amount you want. Okay. Now the process is going repeatedly through load cases 4, 5, and 6. And in this way, we model the cyclic behavior. Okay. Once the last step of the last load case is done, well, the structure has been damaged, and you can see all the response of the structure there. Okay, have said that, I would like to show you the results. Well, first you have to run the structure, but for matter of time, the structure has been run already, and we're gonna load the results. Okay, let's load the results in the cyclic case 1, and in step around 50, 150, for example, the step 50. Let me look for here. Let me get the information. We are near. Okay, we are here. Good. Okay, now we're going to evaluate, for example, the cracking strain in Z direction. Okay, we load the information. Okay, now we can rotate a little bit the model, and we can observe how with the software we can capture the cracking strain, and we can evaluate those zones of the joint where the extent of cracking it's gonna initiate. Of course, in this step, cracking has been already initiated. Okay, but we can see how it's going to be increasing, and which is the spread of the pattern. Now, for example, let's see another step. It could be maybe the step 1 in the cyclic load 2, for example. Okay, that would be here. I'm going down a little bit down. Okay, okay, there. 101. That's good. So we can see here that this zone of the column is the most demanded. For example, now let's see the X component of cracking strain. Okay, there you can see that at this time of load, we have the propagation of the strain, the cracking strain in X direction of the elements. And well, you know, as we already know, there are different models and different methods for capturing the plastic or inelastic behavior, but sometimes the plastic hinge method has to be calibrated with real test or real models. Because why? Because plastic hinge models can capture the inelastic rotations, taking into account the degradation in elements due to crushing and cracking, but the power of this kind of model, that distributed plasticity, is that we can see and we can get the point, the exact point of initiation of cracking or plastic or inelastic behavior. And well, the advantage of here is that we can use, we can reproduce our models for calibrating whatever other model we have. If we have tested and we have calibrated this model with a real test, we can use this model easily for calibrating another behavior, such as plastic hinges, fiber elements, uh, or fiber LL, or hinges with defined lengths, whatever model we're going to use. Okay, now I would like to show you the X direction plastic strain in steel. I'm going to hide here, but now we're going to see the plastic strain in X direction. Let me get here. Okay, here we have. Okay, there you can see I'm going to rotate a little bit the element. And now you can see here the information which is matching with the cracking very after cracking. We have the bars that have yield, and now we are capturing, we are watching the real behavior and the real deformation once the reinforcing bars has yield. And with this information we can apply a very close attention of those zones where we now are watching the real sound where of those bars that are yielding. In this case, we have this information here. We are watching that the yielding is spread in this zone, but maybe there are another areas of the member that could be of importance for us for our evaluation. And well, this is a powerful tool. This is a powerful tool for us to, for making forensic engineering, for example, here we have a real test. Okay, well, a real test now. This is a real failure. Okay, and we can see that those zones of the joint, if the most demanded, and we have proved it by the software. So we have a lot of yielding. We have a great failure, a share failure there, and well, once we have calibrated these models, well, we can see that we can test and we can perform whatever analysis we want. Okay, so now let's see that in this example we made 5 cycles. Okay, 5 hysteretic cycles. There you can see the deformation, force deformation curve. Okay, for each of the cycles. In the next slide, we're going to see that starting by the cyclic behavior, we have the cyclic envelope. We already know that when we're going to make assessment of existing structures and we're going to evaluate the inelastic behavior, okay, all our models, no matter what kind of model you are taking into account, it could be a hinge model, fiber model, finite element with distributed plasticity, you have to make your improvement criteria, and you have to make your model parameters in terms of the cyclic envelope curve. That is this one, the orange one. So basically, so we can conclude here that if we're going to make any other assessment or another type of analysis, we can use this software for generating the cyclic envelope, where we can get the loss of strength, the loss of rigidity for our models. Okay, now we're going to the next. If we make a pushover analysis, you know, the gray one, the gray curve, which is going forward, this curve gives us a little more energy to dissipate. And this is why, because the pushover, okay, the load increasing, like monotonic loading, you know, maybe cannot capture the degradation and the loss of the stiffness due to crushing and, you know, buckling of the reinforcing bars, and the cyclic behavior can capture more accurately this information. And well, we can gather all that information and we have the point for comparing. Okay. So, well, to this moment, I don't have nothing more to say than thank you for your time. Thank you for being with us and share this moment of as we say, a moment of knowledge. And well, I would like to know if you have further inquiries about the software, the model. I would like to know what you think about this presentation, if it was useful. Okay, very well. If you have no inquiries on that, I just want to let you know that I want to let you know that your PDH are going to be sent by email to your account. Thank you very much. Thank you very much for your comments. And well, basically, as I was telling you, you will be receiving your PDH by mail as soon as possible. Okay, and well, I just want to let you know that every Monday we'll be presenting different real cases, real situation that we have modeled with civil fam. And well, it would be great if you could join us and well, enjoy a little bit of knowledge because every day and in every webinar, all of us, we are learning a lot. Okay, well, thank you very much for your time. Have a good night, and I hope you can join us in our next presentations. And well, you're really welcome. Thank you very much.